Good morning and welcome to ECMath. Today we're going to go over the basic individual transformations that might happen to a function. There is a companion worksheet to this. I will post a link in the show notes, and if you're one of my students, you should be able to access it. It's the back of the worksheet that was used in the previous video as well, so you may already have it printed. So the main idea of a transformation is that if we have some function f of x, we can add coefficients and multiples, adding, subtracting, multiplying, to all sorts of various places in the function. We could add a coefficient in the front. We could add a number onto the x. We could subtract a number inside the parentheses or add, and we could also add or subtract a number outside of the parentheses. We could also have positives or negatives in the front and positives or negatives on that b value attached to the x. Those are 6 possible transformations then that we might see. Those are all on this page. Looking at this worksheet, I've grouped them in the following way. Rows are the different types of transformations. We have reflections, shifts, and stretches. Columns are transformations that affect the inputs or x values, and then transformations that affect the outputs or y values. So that's how this sheet is organized. And we usually treat input transformations and output transformations a little bit differently. The second column, even though it comes second, is probably what you're most familiar with, transformations that affect the y values. And the input transformations might be a little less familiar. We're going to go just in order of the sheet, from bottom left to right, bottom to top. Let's begin. So the first transformation is going to be a reflection of the function over the y-axis. In function notation, we see this as f of negative x, or opposite x. So what that's going to do is whatever x value you put in, it's going to take its negative before the function is applied. Here are 2 examples. The square root of negative x and the absolute value of negative x. So for the square root of negative x, I'll first draw the parent. I'm going to just sketch the parent. If you're not sure what the parent graph looks like, consider watching the previous video one more time. Now let me draw the reflection of that. So if I have x, when I think about this negative x being there, that's going to move that x to the other side. And it's going to do that for every point on this graph. So whatever point I had on the positive parent, you'll have on the opposite of that. You're taking all of the x values and multiplying by them by -1. And this graph would be the square root of negative x. For the graph of absolute value of x, let's take a look at that parent graph. It would look like a V. I'm not worrying about scaling on the axes here, I'm just thinking about the shape mostly. Now if I take that graph and reflect it over the y-axis, it's going to look the same, and that's something that can happen with a reflection over y, is you do have a reflection, you did mirror this graph, but the graph has some kind of symmetry already. So this is actually, in red, the graph of y equals the absolute value of negative x. Just so happens that's the same as the absolute value of positive x. Whenever you see a negative inside the function attached directly to the x, that's going to be this reflection over the y-axis. The next type of transformation is a reflection over the x-axis, which we consider a vertical reflection. That is written like y equals negative f of x. So it still uses a negative, but the negative is on the outside of the function now, whatever that function might be. The 2 examples are negative square root of x and negative x squared. Let's graph those. So for negative root x, I'll first sketch the parent. That would be the parent. And then the reflection of negative root x over the x-axis would take all the y values. So to say that this was the point 9 and 3, that point would map to -3 and 9. It would be down here. And every point on the graph would have this same property. So that will be reflected over the x-axis. This is the graph of negative square root of x. For negative x squared, similar thing. Your parent function looks like this. The entire graph is reflected, 0 does not reflect, but everything else is reflected. So this will be that downward open parabola. Sometimes for functions like y equals x squared, it can be difficult to tell if the negative is inside the function or outside the function, but it's obviously a very important difference. This negative is outside the function because there's no parentheses around the negative. So if you follow, orders of operation, you do exponents, and then later on you do multiplication. This negative is really like -1 times x squared. So x squared happens first, and then the -1 flips all the y values of that parabola. If this was going to be an input transformation, that is the other type of reflection, it would have to look like -x, close paren, quantity squared. That's not what we have here written. That's different. That would have been the other type of reflection. Yeah, and that happens with x squared. That's a very common question. Just look for parentheses. If the negative is just out in the front, then it's usually that x-axis reflection, not the y-axis reflection. With a symbol like the square root, it's really clear whether the negative is inside the root or outside the root. Here is another file I will share with you in the show notes. This is a Desmos file that contains all of the different reflections that you might see. And what I've put on here is a function that is not one of the common everyday parent functions. It's a piecewise function that I made up from my own twisted mind. And that's because you can actually apply all these transformations to any kind of function you want. You have to do a little bit of technical wizardry. I can explain this if you are curious, but not in this video. That reflection over x on this function looks like this. The parent function is dotted, and the reflection over, I said x, this is the reflection over y, looks like this. The reflection over the x-axis, which is affecting the y values, looks like this. Get my camera out of the way. And you can actually reflect over both the axes at once. You can have multiple reflections, and that would look like this. But usually we'll start out by doing one single reflection. So here's that reflection over x, and here's the reflection over y. All right, let's talk about shifting graphs. This is an input transformation that you probably have seen before if you've put parabolas in vertex form, but this applies to all kinds of graphs. So if you're going to shift horizontally by c units to the right, I should say left here. Sorry, that should say right. It's going to be y equals f of x minus c. And what you'll notice is that a shift to the right actually correlates with a negative number. We've seen that before when you put parabolas in vertex form. And here's our first example. So y equals parentheses x minus 2 squared. Notice that this minus 2 is in those parentheses before the squared. That's like telling you it's an inside input transformation. So this is going to move this 2 units to the right. So if this was your parabola looked like this, there's your parent. Your vertex would go 1 and 2. It would be at positive 2. Opening up like this. You can also do this with x plus, with any other graph. So here's a square root of x plus 3. So you can think about this as the square root of x minus 3, which means that this is going to go minus 3 units to the right, is one way to think about it. Or you can just think about it as moving 3 units to the left. So if your parent function for square root looks like this, count 3 units to the left, 1, 2, 3. Plot that 0 point. Plot your transform square root curve. This is the square root of x plus 3, moved 3 units to the left. The note on the bottom says the same thing. The direction of a horizontal shift is the opposite direction of the sign. X minus c will move you to the right, not the left. One way to think about this is that in this transformation, if x equals 2, then in the paren you'd have 2 minus 2 squared, which is 0. So the point of the parabola where y equals 0, that is the vertex, has to occur when x equals 2 in the transformed equation. So it's kind of like you're plugging in x values. You need a larger x to satisfy the 0 part of the equation to make the parentheses 0, because you're subtracting 2 before you square that number. That's why these input transformations often work in what we would say backwards fashion. Similarly, we can do vertical shifts of functions. So we can move functions left and right. We can also move them up and down. Those look like y equals f of x plus d. And what you'll notice is that that plus is now outside of the function or outside of the parentheses. So 2 examples, y equals x cubed plus 4. And again, right, this is like x is in parentheses, plus 4 is outside. And y equals x minus 2. Now this one's a little weird. We'll come back to that. Let's do x cubed plus 4. Remember your video from last time? What does x cubed look like? Something like this. Has that inflection point at 0, 0. So if you move that up 1, 2, 3, 4, you can also move every other point on the graph up. For x cubed, let me zoom in a little bit. I like to remember that there were sort of 3 key points right around 0 on the graph of x cubed, and I'll move all 3 of those points in that same relationship up. And then that helps me sketch the smooth x cubed curve. So this would be x cubed plus 4. Let's look at y equals x minus 2. So this is not something that was on your transformation sheet, but the parent here is the line y equals x. So then we have the line y equals x, that's the inside, and I'm taking away 2 from that. So this will take the line y equals x, which you know and love, and move everything down 2 units. So -1, -2, and keep the points in the same orientation. It turns out that everything you've learned about lines, right, mx plus b, y-intercept, slope-intercept, point-slope, it can all be thought of as transformations as well as input and output transformations of some parent y equals x. And that's why I wanted to put that here. So this was a downward shift of a parent line, and that's the vertical shift. We can go flip over to the Desmos activity and look at these both types of shifts. So here's our parent graph. We'll first do the input shifts. I'm going to move this slider, and you can see this shifting horizontally. Notice that as I move the slider right, the graph shifts horizontally left. As I move the slider left, the graph shifts horizontally right. That's that x minus c coming into play. Let me put this back to 0. I'm going to shift up and down by moving the d value. Notice that as I move the d value right, the graph goes up. As I move the d value down, the left, the graph goes down. That's like sort of the direction you'd expect. A negative d value moves the graph down, positive moves the graph up. Notice when I do the vertical shift, nothing happens to the x values. And when I do the horizontal shift, nothing happens to the y values. They stay the same. That's why we call these like input transformations versus output transformations. They affect each set of values differently. The next set of transformations is probably the most challenging, and they're what we're going to call dilations. You've perhaps called them in the past stretches or shrinks of a graph, and we can still call them that, but just I would say the more official term is dilations or vertical transformations. And we're going to be really careful isolating what a horizontal dilation looks like versus a vertical dilation. Often those get confused with simple graphs, but it's really important to know the difference. Let's look at the horizontal ones first. So in function notation, these are done by having a b value attached to the x. So something like f of b times x. In the 2 examples, you can see I have 1/2 x parentheses closed squared. And I also have the absolute value of 3x. That 3 is in the parentheses. Like the shifts, these also work in the way, like backwards, I guess. So when you have a b value attached to the x, you actually divide all the parent's x values by that b. So a 1/2 x squared, you might think that's going to be a shrink or a compression. This is actually a horizontal stretch. And 3x, you might think, well, that's going to be a stretch. This is actually a horizontal compression. Or a shrink, in that less formal language. So let's start with the parent. In this case, the parent is x squared. And I'm actually going to draw a couple key points on x squared here. I'm going to be a little more precise with the parent. One half x squared says that you divide all the x values by 1/2. Well, 1 divided by 1/2 is actually 2. So the transformation of this is a horizontal stretch by a factor of 2. So if this was at 1, this point right here is going to move out to 2. And this point right here is going to move out to -2. 0 does not stretch anywhere. So this will be sort of a wider parabola. A 1/2 stretches a graph by the reciprocal factor. On the other hand, 3x will shrink all the values down. So if I draw absolute value x, maybe look like this, look like this. I have a 3 here, so I'm going to count out to 1, 2, 3, and like put that point on my parent, -1, -2, -3. Put that point on my parent. Try to get them sort of matching. There we go. When I plot absolute value of 3x, you can think about what would happen to an x. If I plug in 1, the first thing that happens is I do 3 times 1, and I get 3 as the output. So I sort of needed less x in order to get the same y. That's why this actually takes these values and brings them in. And this is going to result in a v that is wider. 0 doesn't go anywhere again. This v is wider. Did I say wider? I meant narrower. It's going to be narrowed in by a factor of 3. I guess you could say a factor of 1/3. This is a horizontal shrink. So I took all of the x values and divided them by the b value of 3. So I'd say this is a shrink by a factor of 1/3. This is a stretch by a factor of 2. Let me flip over to Desmos and just look at that horizontal stretch and shrink again. If I have my graph and I increase the b value, look, I've got my b slider, I'm increasing the b value, that is going to compress the graph further in towards 0. It's further in towards 0. And specifically, let's set the b value to be a specific number of 2. I'm going to zoom in so I can see my grid lines. Notice that at this point was 2, 4. On the new graph, it's 1, 4. That is, every x value is being divided by 2. This local max was -1, 1. That's now -0.5 and 1. The y values don't change. Only the x values change when you do this transformation. If you make the value larger, or you make the b value smaller than 1, so here's b at 1 again, and let's make b 1/2. You can see how this gets wider. Let's make b 1/4. If b is 1/4, all of the x values are being divided by 1/4, or you could think about it as being multiplied by 4. So a value that was at 2 here, an x value that was at 2 will now appear at 8. All the x values were multiplied by 4 or divided by 1/4. That was probably the most challenging type of transformation. Let's now look at a vertical dilation or stretch or shrink. That's accomplished by having a multiple attached to the front of your function. So it's multiplied to the front of the function. Sometimes that's combined with a reflection, like if that a value is negative. But here, let's just assume the a value is a positive number, but it could be greater than 1 and it could be less than 1. So you could have a stretch or a shrink depending on that. So if I have y equals 2 root x, what this is going to do is multiply all y's by 2. So think about your parent function of square root. I'm going to do like I did before and put a couple specific values on here. So here's 1, 1, and here over here we'll say is 4, 2. Make that a little lower. That's the parent. Ooh, we were doing dotted lines, weren't we? If I multiply all the y's by 2, the point that was at 1 will move to 2. The point that was at 4, 2 will move up to 4, 4. And this will be a vertical stretch. This is 2 square root x, the vertical stretch. And then finally, let's look at 3 cosine x. What? Cosine? I didn't know trig was on here. It's really nice to look at vertical stretches with some trig values, some waves, just because they have that nice sort of symmetry. So this is going to take all the y values. It's going to times the, we're going to say multiply. That looked like an x. Multiply all y's by 3. So cosine x started at 1, and it did some of this action. If you multiply all your y's by 3, that'll go up to 3 and down to minus 3, keeping the x values all the same. So that's an example of a vertical stretch or a vertical dilation. Let's flip over to Desmos and take a look at that one as well, just to finish the set. So this is if I change the a value here. And first I can stretch something. That's an a greater than 1, is a stretch in this case. So it is not acting backwards here. This is just affecting the y values with straight up multiplication. And then if I have an a less than 1, this will compress this vertically. Notice as you compress something vertically, it looks like it's getting wider, but it's not actually getting wider. Instead, what's happening is the y values specifically are changing. What was at 2, 4 is now at 2, 2. What was at negative 1, 1 is now at negative 1. X stays the same. Y is 1/2. So you're dividing all the y values, multiplying all the y values by 0.5. You're dividing them by 2. So that's the vertical compression. You can get really small. You can get really tall. Those are the vertical compressions and stretches. And here they are in comparison to the horizontal stretches and compressions. So you can see the difference between horizontal compressing and that vertical compression. Just to recap, we've looked at reflections, both over the y-axis and x-axis. We've looked at horizontal shifts and vertical shifts accomplished by adding or subtracting a number somewhere in the expression. And we've looked at horizontal and vertical dilations accomplished by multiplying a number somewhere in the expression. We've also separated these, looking at which functions affect the x values, which is the first column, and which transformations affect the y values, which is whatever happens in the second column. The next thing to do is start combining these transformations into sequences where you might do 2 reflections and a shift and then a stretch. But that we'll have to do another time. Thank you all for watching. Please let me know what questions you have in the comments, and I'll see you all next time.